Greetings, calculus students. So in the last video, we learned about indefinite integration and how when we have an integral, and we need to take the integral and to find the area under a graph, what we really need to do is find the antiderivative. So we're just going to be focusing on strategies for finding the antiderivative. So you can see these problems kind of go from easy to more difficult. And for A and B, we're just going to be using similar strategies to what we did before. So if I'm trying to find the antiderivative here, it's like I'm taking the indefinite integral of both sides because I want to find the general antiderivative. And so using this as kind of my help with the notation, I know that the antiderivative of f of x is going to be big F of x. And then I can kind of do a little guess here based on what I know. Maybe the 2 should stay, and then I have x squared. We can always check our work using derivatives. So if I check real quick, f prime of x, here I would get 4x, which is too much. I only want 2x. And so it seems like instead of keeping this 2, I need to get rid of it. And so now when I check my work and I take the derivative of big F, I get 2x, which is what I wanted. Woohoo! The only thing I need to add is my plus c. So don't forget that plus c when finding your general equation. Okay? So we're going to do the same thing right here. The notation, the antiderivative for f prime will be f of x. And then we can have my x, and I think it needs to become a squared. So down here, I will check my work by taking the derivative. So f prime of x here would be 2x. So I have this 2 that I don't want. But to get rid of it, I could divide by 2, and then it's 1, just like the 1 that I want. So I'm seeing that in my antiderivative, I need to include that 1/2. Because then the 1/2 and the 2 cancel each other out. And then don't forget your plus c. All right. With problem C, this strategy of like guessing and checking isn't going to work so well. So I feel like we probably have a good idea of how to find antiderivatives, but C is a mess. Look at all those fractions. So we need more of a strategy. And what we've kind of been doing here is using what we know about the power rule for derivatives and kind of doing the opposite. So that's what I'm going to take some notes on right now. We've been doing the opposite of the power rule. We've been doing the opposite of power rule. Okay? And so if the power rule for derivatives, like we did here, means that we bring down the exponent, so we brought down the exponent and changed the exponent to 1. We need to do the inverse steps of that. So instead of multiplying by the exponent and subtracting by 1, we're going to start by adding plus 1 to the exponent. And then instead of multiplying by the exponent, we're going to divide by the new exponent. So if you think about it, these are the inverse steps to undo the derivative. We're undoing the derivative. And so what this looks like notation-wise is if I have f prime of x equals a to the times x to the n. So this looks like any sort of power rule function. As we know, sometimes with power rule we have coefficients in the front. That's just a random constant. So to take the antiderivative of this, to get f of x, we would keep the constant in the front. We're not really messing with that. Our new power, we would add 1 to it, and then we would divide by our new power. So here is our division by the new power. So this is the opposite of the power rule that we're going to use to take derivatives. So that's what we're going to apply to this problem C. Okay, so let's use those steps. So the antiderivative of big F prime is just big F. My constant, I'm gonna not mess with that. my new exponent, I need to add 1, which is the same as adding 7 over 7. Okay, so we're adding plus 7 over 7, which is the same as adding plus 1. So our new exponent will be 11 sevenths. And then we need to divide by that new exponent. So dividing by 11 sevenths is the same as multiplying by 7 over 11. Okay, so I think this is my antiderivative, but just as we did before, we can still check our work. So if you feel uncomfortable, you can do a quick check. So the derivative of big F of x, we'd keep our constant the same, and I guess we have this number 2. We'd bring down the derivative, or the exponent, and multiply it by. So we'd multiply by 11 over 7, and then we'd subtract 1 from our old exponent, and subtracting 1 from 11 sevenths would give us 4 sevenths. And so obviously these fractions would cancel out with each other, and I'd be left with what I originally had, 2/3 x to the 4/3. And so when I take the derivative of my antiderivative, I get what I started with. So I know that this is a good antiderivative. I just have to add my plus c. And there it is. Beautiful. All right. So then moving on with this, you could see I already have a little note there. So just like when we did derivatives of power rule, sometimes we had to rewrite our fractions to make it easier to take the derivative of. Same thing with antiderivatives. So I had 1 over x squared. I'm going to rewrite that as x to the negative 2 so that it's easier to take my antiderivative. So the antiderivative of g prime will be g of x. I will add 1 to my exponent to get negative 1, and then I will divide by my new exponent. So, plus c, I can simplify this a little bit and rewrite it as negative 1 over x plus c. Again, if you're unsure of this, go ahead, work the other way, take the derivative, and you should get positive 1 over x squared. Okay. So lastly, we're ending with a derivative where I'm not so sure if I should do the opposite of the power rule, but let's see if it works. So my variable, the antiderivative of dy dx, would just be y. So if this is cosine with a derivative, or an exponent of 1, then my new exponent would become 2, and then I'd have to divide by that new exponent. So let's do our due diligence and check this work. So if I were to check this, right here, y prime, or dy dx, I'd bring down the 2, and so 1/2 and 2 cancel out, which has to get 1. That's good. But I'd have to use chain rule. So when I do the power rule, the inside function cosine of x would stay the same, which looks good so far, but then remember I'd have to multiply times the derivative on the inside. So my inside function is cosine, I still would have to multiply times the derivative of cosine, which is negative sine of x. So this isn't the derivative that I started with. So there's a mistake here. We can't just do the power rule. Sorry if you wrote that down. I'm going to erase it. You can just put a big X in it. In this case, we just have to like kind of think about it. Oopsie daisies. So if we think about this, if the derivative is cosine, what function has a derivative that's cosine? The answer, hopefully you're getting, is sine. So when I take the derivative of sine, it's cosine of x, which is what I wanted. Then I'll just add plus c. There's my perfect antiderivative, my general equation. And so, as we just saw in example E, we can't use the opposite of the power rule for everything. We need to have some more rules because there are more functions out there other than just exponents. And so that's where we get to this table right here. So in the first page in this whole packet is a reminder of derivative rules, and now you have some antiderivative rules. But they should look really familiar. So for instance, if we started off with our ln function, the derivative of ln, if we were to go this way, is 1 over x. Or if we had, tangent, the derivative of tangent is secant squared. So all of the antiderivatives are just going the opposite way. So when you see 1 over x, the antiderivative of that, going this way, is ln of x. And then secant squared, the antiderivative will be tangent. So if you can do derivatives, you can do antiderivatives. So I'm going to give you a minute to kind of look over this table because we're going to be using a lot of these functions in the next problem. So please pause me and check off these. Okay, so in example 2, this is an intense example. It's obviously a lot more challenging than the examples we were just doing, but it's also trying to intimidate you. So I can see that there's some simplification I can be doing. Like I have x as the denominator in both these fractions, and I'm seeing a lot of x's in the numerators that I can simplify. So we've got to do a little work before we're going to take the antiderivative, but it will make all of our antiderivatives a lot easier. Okay, so let's write a slightly more simplified version of this. For sine of x will stay the same. And then when I divide 2x to the 4th by x, I get 2x cubed. The square root of x is the same as x to the 1/2. So dividing x to the 1/2 by x to the 1st power, I get x to the negative 1/2. And then x divided by x is 1. So I got that. And then over here, remember to distribute this negative sign. It's going to go here as well as in front of the 1. So I can cancel out my x to get minus cosecant squared of x, and then minus 1 over x, because this negative sign, remember, has to get distributed to both of these things. So I just did some algebra to simplify this. And now it's basically like I have just a bunch of different antiderivatives that I have to take. So just like I could take the derivatives of all of these separately, we're going to be using this rule up here. If I have a lot of different terms, I can just take the antiderivatives of them all separately. So like I have these terms, I'll just take the antiderivative of each of them and add c at the end. And so this is one that I want you to try. So I do want you to pause me and use the table up there to try this. So give it a try on your own. Please do that. And then resume me and you can check your work. Okay, so you should have some sort of answer down there. And if you don't get all of them right, that's cool. If you get some of them right, that's amazing. It's amazing. All right. So the derivative of, or the antiderivative of g prime is just going to be g. My constant in front of sine can stay. The antiderivative of sine is negative cosine. So I write negative cosine of x. And that's it for that one. The 2 can stay. I will add to the exponent and then divide by my new exponent, like that. So if I add 1, my new exponent is 1/2, and then dividing by my new exponent, I'll get 2. The antiderivative of 1 is just x. Hopefully y'all got that one. This one, look up at that table. I know that cosecant looks a little scary, but the antiderivative of cosecant squared is negative cotangent. And then we just talked about this, so I hope you got it. The antiderivative of 1 over x is ln of x. We do have to add this absolute value just because you can't have a negative number inside of the argument of ln. And then plus c. We can clean this up with a little bit of algebra. So my final form that I would write this is negative 4 cosine of x plus 1/2 x to the 4th minus 2 square root of x plus 7 cotangent of x minus ln of x plus c. And that's a beautiful antiderivative. Okay, so yes, these are some rules that you'll have to memorize, but remember, if you can do derivatives, you can do antiderivatives.